So, phase change, phase change. So we've talked about what heat is. We've talked about where heat goes, and a little bit what heat does. One of the things that heat energy does, when I add heat, it makes things get, temperature goes up, makes their kinetic energy go up. When I take it away, kinetic energy goes down. We have this changing temperature. But at a certain point, when I'm adding heat, solids become a liquid, liquids become salt, become gases, and so on. In other words, it changes its form. That's what we're going to talk about in this chapter. We're going to talk about how heat causes things to change form and about that process. And that process is called phase change. We also see change of state. State and phase are synonymous terms. They're just two terms for the same thing. The process where heat energy is added or removed so that the substance changes its phase. This is a physical change. In other words, when I melt water, when I take solid water, ice, and I melt it, is it still water? Yeah. It's still H2O. If I put it in steam, it's still H2O. The one caveat is when we do change it to plasma, there are no molecules. When plasma exists, it's just it's basically bare nuclei and electrons. So as you heat it, there was a chemical change in that process of becoming plasma, because there's no such thing as water in the plasma state. You only find elements in the plasma state. Anyone need more time? So this occurs at the phase change temperature. Phase change occurs at the phase change temperature, the melting point and the boiling point. Whether it freezes or melts, freezing and melting occur at the melting point, boiling and condensation occurs at the boiling point. Thing is, temperature does not change until all a substance has visibly phase changed. In other words, during phase change, if there are two states present, solid water, liquid water, as long as you have both visible, the temperature does not change. Okay? During that whole process, that solution will remain at 0 degrees Celsius on that. I'll come back to this, but I have this little clip. So remember, what we're really talking about here is this, right? We take solid gold, and we light the torch, and we put the torch on it, and notice it becomes a liquid, because I added heat energy to it, and it melts into a liquid. And as soon as I take away that heat source, now because gold at room temperature is normally a solid, as soon as I remove that heat, it's going to see how it starts changing color. You see these colors changing. Because like at the surface there, what's happening is that it's starting to become a solid again because it cools down and things like that. I mean, on the periodic table, of all those elements on the table, there are only two that are going to be a liquid at room temperature, i.e. like 20 degrees Celsius. As bromine and mercury are the only two elements that are a liquid. Most are solids. And there are a few gases in there too. Anyone need more time? So we need to talk a little bit about the phases. Now, if you want to go more in depth into these things, some of the chapters we skipped are these chapters on the various solids, liquids, gases. I think it's like 18, 19, 20, or 17, 18, 19, something like that. But that's in those chapters when we jump chapters. There's like a chapter on solids, a chapter on liquids, and a chapter on gases. But solid has a constant shape and volume. In other words, my hammer, if I had a big graduated cylinder, I could put my hammer in it, and I could get its volume. And I can mass it. This has this shape. Tomorrow morning, when I come into school, do I have a reasonable expectation that this will still have the same volume and still have the same shape? I do, unless somebody destroys it. But I have it's not just. In other words, sitting on my desk, is it going to change? No. Now, the atoms within a solid are within 1 atomic diameter of each other. This is how close they get, 1 atomic diameter. And they're locked together. They're locked together. Remember our conduction, our chain? You guys are in a certain order, right? They're locked together because they're in that crystal. And not all crystals are nice and pretty. Things like quartz have 6 sides and all that stuff. Some are just locked together. We still call it, it's called an amorphous crystal. It doesn't have a real shape to it. But they're locked together, and they're held together rigorously. So if this guy's your partner, so if my hammer's here is one atom and my fist is the other atom, can they ever change places? No, they're locked. They are where they are. They're going to stay there on that. Solids have the lowest energy state for a material. So in a particular material, the solid form is going to have the least amount of energy, least amount of kinetic energy associated with it. Okay. Anyone need more time? And during phase change, it's these little bonds they have to break to make it a liquid. They're also what's forming when it goes from a liquid to a solid on that. You saw that with the ice crystals. Remember ice crystals, when we talk about ice crystals, the bonds form as they cool and things like that. Now liquids have a constant volume, but they take the shape of their container. I mean, here, I have about 500 milliliters of water in my little flask here. Notice what kind of shape does it have? It has the shape of a flask. Well, yeah, it's a cone, triangle, whatever. But it has a flask shape. Now, this is a 500 milliliter Erlenmeyer flask. This is a 1,000 milliliter beaker. What mark is that going to come up to on my beaker? About 500, right? Because it's going to only fill it halfway. So there's a constant volume. But notice, does it still have a flask shape to it? No, now it has a beaker shape to it. Okay, they change shapes. So it doesn't have its own shape, but it does have a constant volume. You might add a thing here. Liquids are incompressible. You cannot compress a liquid. In the world of fluids, this is the big difference between a liquid and a gas in the world of fluids. Liquids cannot be compressed. In other words, I cannot force a liquid into a smaller volume. But I can force a gas into a smaller volume on that. So it has its own shape. Now the atoms are still 1 atomic diameter, but now those bonds that we're holding together, they're free. I can move around. They can move around the solution. So they're moving and moving and moving around. And all constantly moving. Now, let's think. In a solid, can the atoms move a little bit? They can't change positions, but do the atoms move in a solid? You know, they vibrate, right? I mean, that's temperature. That's like kinetic energy. Now they are free to move on that. They are free to move. If you look down that long, I begin to think other things. Don't help. My world, lawyers would get the same punishment as their clients. They're free to move in relation to each other. So they really now, the energy, since they are free to move and they're moving a lot more, they're moving a lot faster, they have more kinetic energy in the solid. But they're going to have less energy than the gas form. Gas form. But remember, at this point, we're still water. Still water. Water's water. We're talking about water. Anyone need more time? Gas. Now, gases not only take the shape of their container, they will take the volume of their container. They'll take the volume. I can compress a fluid. I can force a fluid into a gas. In fact, like little bottles like this, we compress it so much that it actually becomes a solid. You can hear liquid and a solid in there. It becomes, we actually just state. But do I have a lot of gas in this cylinder? Yeah, there's a lot of propane in this cylinder. I mean, if it was just gas, if it was like a liquid, I mean, a liquid, I would only be able to have this much volume of gas. But when I release the gas in here, you know, if I had this camping, could this run my lantern for a long time? Yeah, that's a long time. You know, on that, but you can kind of feel there's stuff in there. Shake it, just pass that around, just don't drop it. Now, they will spread evenly throughout whatever volume. In other words, if I took a gas in a 1 liter container and put it into a 2 liter container, it's not going to just sit in the bottom of the 2 liter container. It will spread out evenly throughout that container on that, and will displace other gases and things like that, at least to a point on that. More energy than liquid. By the way, do you remember U? Do you remember what this symbol is the symbol of? The letter U? What kind of energy? What? Internal energy. Yeah, that's our internal energy. U is our internal energy. Talk a lot about U in this unit. U becomes very important in this unit. Anyone need more time? So these are said. Our last state is plasma. Now at this point, it's just atoms, Okay, there's no compounds anymore. No water. There's no such thing as water in the plasma state. It would be just hydrogen, oxygen loose. This is totally ionized matter. Nuclei and free electrons. Extremely high temperatures. This is star stuff. This is what stars are made out of. Is plasma. Now, most matter in the universe is in the state of plasma, like 98% of it. This is the most common state, not plasma. By the way, this is plasma, very hot. It's not the stuff in your blood. Yes, it's the same word, different definition. From bio, if you talked about plasma, you were talking about the fluid that is in your blood. We're not talking about that. It's star stuff. Because it only occurs naturally in one phenomena. Anybody have an idea what phenomena that is? Yes? Lightning. That's absolutely correct. Lightning. And, by the way, when you see the lightning, it's no longer plasma. Plasma is black. If you were in the interior of the sun, it would be black. Absence of light. Why do we know that? Because we never say anything in the middle of the sun. Because how light is released. Light is released when an electron falls from a higher energy level to a lower energy level. It releases a photon or a wave of light, depending on which theory you're talking about. But it takes an electron going from a higher energy level to a lower energy level. But in plasma, is there any electrons going from higher energy level? No, because they're completely away from the nuclei, so it's black. When you see that lightning stroke, that white comes through, what you're seeing is the air cooling down. And when it cools down, those electrons are rejoining their nuclei, releases light. So you actually, what you see is after the lightning stroke goes through, and then you see it. Well, that's because there's charges in the air and they have different set charges, and eventually you get enough voltage. When we talk about voltage, you get enough electric potential. Let's jump on that. But lightning is the only place it occurs naturally. You can make it go do other things. You can produce it, but it's only going to occur naturally in lightning. And only for a brief second. Here's one of those things. Which gets formed first, thunder or lightning? Thunder. Thunder gets produced first. Thunder happens before it, because the thunder is when that lightning stroke goes through and expands the air. Lightning comes later. Why do you hear thunder after the lightning? Because light travels faster by many times on that. So it's one of those little things. Anyone need more time? We'll talk more about all the stuff we talk about waves. Now, so the energy of phase change. Now we've talked about the energy to make something get hotter or colder. You've done that, and you've seen that in lab, right? When you had the piece of metal in the water got warmer because energy left the metal and went into the water. You've seen the energy go from one place to another. You know, it came out of the hot water, through the bar, into the cold water. Okay, conduction. But at a certain point, now the energy added to a substance between the phase change temperatures, like for water, between 0 and 100 degrees Celsius, causes a raising or lowering of the temperature, i.e. a change in the average kinetic energy. However, energy added or removed when a substance is at the phase change temperature will only cause the substance to phase change only. Why? Because the energy is not going to be made into the kinetic energy in the material. It's going in to do something else. Do we lose the energy? No, it's there. In fact, that something else energy can be released later on, like when a gas goes to a liquid. It's going to be released from a liquid to a solid. It's going to get released. Anyone need more time here? So, this diagram, good diagram for your notes. Maybe several diagrams for your notes. So, energy is absorbed. So, solid absorbs energy, it becomes a liquid. Liquid absorbs energy, it becomes a gas. Conversely, it's released when we go in this direction. You know, this is one of those reasons why steam heat is so good, because we release an enormous amount of energy. When the steam goes to a liquid, it's going to release energy to its environment. Okay, you can release it, which is not always good. It can be good in some cases, not good in others. I know for some cases, if you've been around someplace just before it starts to snow, anybody ever know? You guys probably don't ever notice this, because you're probably not around places where it snows a lot. But just before it snows, you know what happens to the air temperature? It goes up. It's a little warmer. Well, let's say those ice crystals, the water is becoming snow. It's freezing, right? Well, where's that energy going? It's going into the it's going to the air. So sometimes you depend on this. You got to snow, even here when it rains, is it, you know, if it's been, now right now we have this offshore, we've been keeping this offshore closed. It's been a high over the deserts. And the air basically is moving that way. And because it's moving that way is why it's warmer. But when we have a normal pattern on clear days, is it usually a lot colder on a clear day? Yeah, when it rains, does it warm up? It warms up because there's a lot of energy in the water, storms. Snow is the same way. When it's really, really cold, if you were someplace that was like really cold, like minus 15 Fahrenheit, would it be snowing? You know, really when it gets really cold, it doesn't snow. You know, snow, you know, needs some of that, because this usually means clear weather, really cold. Very little water in the air. Anyone need more time? Please, the phase change diagram. Now we're going to be writing this one down a couple of times. You need this diagram because we're going to put information on the diagram. Now this is the phase change diagram for 1 gram of water. The numbers here represent 1 gram of water. Okay? So we go here. We start with some ice at minus 50 and we add some energy to it. And we get to right there. Now at that point, it's all solid, right? This is our solid region where we are a solid right there, solid ice. I get to this phase change temperature and I add energy. Notice we're going to add 80 calories. This is calories down here. We're going to add 80 calories of energy. And by the time I get to the here, but notice during this whole time I'm adding that extra 80 calories, what is happening to the temperature? Staying the same, not moving. Until we get to this point in which we have all liquid. Now in between here, in this region, we're going to have solid and liquid. depending on where we are in that process. Obviously, as we start with a little bit of liquid, and then the solids slowly change to liquid until we get to all liquid. When we get to the all liquid state, here, we start to heat up. To go to 100, so we get to here, right, at 100 it's all liquid. But during this region, it's our liquid region. Now it takes 100 calories to get from 0 to 100 degrees. But notice, once I get to 100 degrees, it starts vaporizing, another word for boiling. And it changes till we get to this point where it's all gas. It takes 540 calories to do that. So it takes a lot more calories to cause something to boil than to melt. This is because gases are far apart. When you talk about gases, when something comes to gas, remember liquids, are they kind of touching? Remember that one atomic diameter? Gases are many atomic diameters apart. So to melt something, I just have to break the bonds because they're still pretty much touching. But now when I do that, now do water molecules like to grab onto each other? Yeah, water is one that likes to grab onto each other. What forms like the meniscus in the water, when you pour the water up, right, you go above the edge of the glass because the little water molecules like to stick to each other. It takes a lot of energy to pull them apart to make a gas, because when you're a gas, you're a long way apart. Now, it's always what these gas molecules are far apart. Most of gas is a lot of what in between? S word. Space. Yeah, there's a lot of space in between gas molecules. There's a lot of empty space. So it gets to this point. Now remember, in this region, we're going to have gas and liquid. Gas and liquid. In fact, I'm going to do a demonstration probably next time to show that this really does happen when we have both present. And here, it'd be all gas. You notice where I have more energy and my temperature is going to go up. But it's not until I can get rid of all the water that I can get it to go up. This fact is very important to steam engines. Because like in the Missouri, we use what's called superheated steam. In other words, as long as there's water in with the steam, liquid water in with the steam, I can only get it up to 100 degrees. Which means I can only put that much energy. Now, what I use the steam is when the steam hits the turbine, like in a power plant, the energy of that steam, that thermal energy, is converted to mechanical energy. We're going to talk about that. That's chapter 24. We're going to get to that. But to get more energy into it, I basically have to get rid of all this water. And that's when I finally can heat this up. We call it superheated steam. Superheated steam. A lot of energy in that. All right. Questions? Anyone need more time with the diagram? We're going to be doing another one of these here in a minute. We're going to put some formulas on it. Now, so it leaves us this idea of latent heat. Now, there are two kinds of latent heat. Latent heat of fusion, where we melt and freeze, and the latent heat of vaporization, which is for boiling and condensing. Our symbol is a capital L. Our unit is either the joule per kilogram or the calorie per gram. And if it's the latent heat of fusion, we put a little F subscript on it. If it's the latent heat of vaporization, we put a little V subscript on it. Fusion is another word for freezing. Now, this is the amount of energy to phase change a given amount of mass. In other words, this amount of energy I add to phase change it. It's the amount of energy I remove to phase change it. Okay? So these are our values. These are kind of like specific heat. Like you have specific heats for different materials. Well, we have different latent heats depending on what the material is. Now for water, latent heat of fusion is 80 calories per gram. Latent heat of vaporization is 540 calories per gram. Notice we've seen these numbers before, haven't we? They're on that diagram. Remember, this diagram is 1 gram. In joules, this is 333 1,000 joules per kilogram. For latent heat of vaporization is 2,260,000 joules per kilogram. Let's think about this number. Now we know a joule isn't a large amount of energy, but still, is 2 million joules a lot of energy? Yeah, it is. 1 kilogram of steam will give up this many joules when it condenses into water. Think about steam radiators for heat. When the steam comes through the radiator, it condenses from steam into water. It gives up this energy to the room. Your room is going to get nice and toasty, warm. You know, my college was heated by steam. And there was a big steam plant. There's a central steam plant on the campus, and all the buildings were fed steam through pipes on that all over the campus. What would be it for you if there was a block in the steam line? There was a block in the steam line just past my room. So my room, senior year, and then the next room out beyond mine was the last room on that line. There was a blockage, so they like froze to death. They froze because they got no steam. Naval Academy. They got no steam. Trouble is, the steam stopped at my room. My room was like a sauna. We would open, in the middle of winter, we had our windows open because it was too hot. I mean, it was like 0 degrees Fahrenheit outside. We had the windows open because it was too hot in our room. You know. So this is what can happen with heat. But you know, I was like, I never had a room that didn't have heat on that. So it was nice. But we can see a lot of energy in water. Again, a lot of energy stored up in water. How does this work for our diagram? How does this work with things? Well, remember, when I want to heat something up, remember I had this formula, right? Mass of the water times specific heat times the change in temperature. Now, for phase change, would this formula work? Because what is the change in temperature during phase change? 0, right? Start at 100, end at 100, which means you would say, if I use this formula, I'd say, oh, it takes no energy to phase change. We know that's not true. It takes a lot more energy to phase change than it costs something to heat or cool. So instead, that's why we have latent heat of fusion. And so the heat of phase change is equal to the mass of the substance times the latent heat, depending on what it is, either fusion or vaporization on that. They both work together. You have to take it in steps. We need more time. So we go back to our diagrams. You want to make a new diagram because we're going to do some things to this. Now, the most important thing is every change in slope in the graph is a separate process. In this graph, how many times does it change slope? 5 times. Slope 1 changes slope 2, slope 3, slope 4, slope 5. So if I wanted to go, say, from minus 50 to 150, how many steps would I have to take? 5. Because you might recall, is the specific heat for ice and the specific heat for liquid and the specific heat for steam, are they the same? No, remember, they're all different. They're different, so we have to take that into account. In other words, I can't say, oh, I'm going minus 50 to 150. Well, that's the delta T of 200. You know, so mass times 4187 times 200, that's going to give me the right answer. Wrong. You wouldn't even be close. You would not even be close. Because probably in here, there's more energy involved in this part than all the other parts put together. It takes the most energy to pull them apart on that. Again, why there's so much energy in that. You know, you look at the old days of steam engines. You look at a train now, you have like for a big long train, you might see 3, 4, 5 diesels pulling a big long train. You know these big steam engines, you know how many of those big steam engines would pull some of these big long trains? 1. In a mountain you may have 2 in mountain regions. And even in mountain regions for the diesels, they have those 5 diesels in front, they put another 3 or 4 in the back, push them up the mountain. Things like that. So here, at this step, so this part right here would be MC delta T. C for ice, right? Because if you have a non-zero slope, you're going to use this formula. Good way to remember it. Non-zero slope, use this formula. This section, Q equals MLF. Now, is the mass the same? If I was doing this problem, would the masses be the same? Yeah, so it doesn't change the mass, it just changes on that. So I phase change it. That would be that right there. Then onto this part again. So we're back to MC delta T, C for liquid water. So this is like 2100 joules per kilogram degree C. This is 4187. This one's like 2050 on that. We get up here, this section, Q equals MLV, latent heat of vaporization. And then our last section, Q equals MC delta T, but C for steam, or gas. All right, this would be true for any substance. So in other words, what would be the energy it took? I would have to add this one, plus that one, plus that one, plus that one, plus that one. I'd have to add them up. But notice, every step I have to do a separate thing because things change. The C's are different in all of the delta T steps. In all these 3 bottom steps, the C's are different. Even the L's, the top, the L's are different. Yes, ma'am. Well, if I just want the energy of phase change, that would be that one step. I mean, that's what this is. Q equals ML. Q equals ML is the energy of phase change. Depending on whether I'm talking about melting or freezing would be here. Boiling or condensing is up here. That's what that is. This is changing its temperature. This is heating it from 0 to 100. I didn't say that. I didn't say that.
So if it goes from steam to liquid, then we have to put a negative sign.
It'd end up being a negative sign.
To show which direction.
Yeah, which would be losing energy on that. And we need more time. So let's talk. So we're going to end our day. We're going to talk about the various processes, various processes. The lab we're going to do. We are actually going to be finding the latent heat of fusion of ice. That'll be the lab that we do. We'll do the burning of the Cheerios one later. Now, melting and freezing occurs at the melting point, MP. Now, the melting point is the temperature at which something freezes, becomes a solid, and it's the temperature at which it melts, becomes a liquid. We just call it the melting point. Well, it doesn't matter what direction you're going. If you were going to look it up in the book, Chemistry Handbook of Physics, it would say melting point. But both processes occur at that one. It's the phase change from solid to liquid and vice versa. Crystals are being broken or formed. In other words, when you melt something, the energy is breaking those bonds. That's what it is. And it's releasing that energy. So you have to add energy to break the bonds. This is why you have to heat it up. The energy goes into that. Conversely, when those bonds form, they release energy. They release energy out. When you freeze something, the energy is released on that. Freezing is also called fusion, hence the term latent heat of fusion. There's nothing to do with, again, another not a radioactive word. Fusion. Latent heat of fusion is what you do here. Anyone else? Yeah, with that. Condensation. This is gas to liquid. Gas to liquid. This is a warming process for the surrounding materials. In other words, when the gas condenses, the energy is going into the environment. In other words, when it goes from a gas to a liquid, all that energy is going out into its environment, going around. Now, this can occur at temperatures below the boiling point. Like it usually does. However, the average kinetic energy of the molecules involved have an average kinetic energy that corresponds to the boiling point. Remember, when I say 100 degrees, that corresponds to a certain amount of energy, right? And there is an energy value to 100 degrees Celsius. So these individual molecules in the air. Now in the air there are water molecules. There are actually liquid water molecules in the air right now. But they're really, really small and you can't see them. This is humidity, liquid water. That's what you see in the clouds. When you see the clouds, that's liquid water. It's not gas, liquid water. You can't see gaseous water. Steam is invisible. All steam is invisible. If you can see it, it's not steam. In fact, this is why, for a steam leak, if you had to go search for a steam leak, you use a broom. You have a guy in a little metal suit. And he'd take the broom and he'd run it along the top of the pipe, and he waits for the broom to disappear. When the broom disappears, found the leak. It disappeared because it vaporized. Which is why you don't run your hand. Run your hand across it, guess what happens to your hand? It vaporizes. Then you don't bleed yet because the stump basically is cauterized and closed. But it hurts a lot, as you might imagine.
Well, you won't be fine, but like...
You probably won't die, but you probably wished you had. I mean, it hurts a lot. In other words, you have no hand anymore.
I'm just talking about like...
No, I mean, your whole hand is gone. You're gone. You have a stump.
What if it was just like fingers?
Well, then you'd have stumpy fingers.
But it would just cut off like...
Whatever part of your flesh went into that steam line, that little steam leak, is gone. It is now vaporized.
But you said it like, kind of covers it up.
Well, no, it cauterizes the wound. Like burns it closed.
Yeah, so you won't bleed that.
Yeah.
You'll be fine, Brian.
Be fine.
Do it. Just
Do
do it. Not
Yes. Gone. That's why these are broom. You know, because usually in these conditions, it's not one of those things. See, the trouble is that, like in a civilian plant, if you're a stainless steel plant, you'd probably just sit there and wait for it all to stop. Usually in the Navy, in the military, it's usually not an option to stop and wait for things to happen. It's like fighting fires in the engine room. You know, the civilian fire department, if you were in port, you got a fire in your engine room, they would give you equipment, but they would not fight the fire because they said their thing would be just close the hatch and wait for it to burn itself out. That's not an option. You know, so they would give us equipment, we'd have to fight the fire ourselves, although we were probably a lot better at it than they were because we trained to do it. If you ever go to the firefighting school at Treasure Island, you go to Treasure Island out there in the bay, there's a firefighting school. Those buildings out there basically mimic engine rooms and boiler rooms. And you would have to go in there and fight the fire. And there one time going there, we couldn't find the fire in the building. You know, so it took us a long time to find the fire in the building to begin with lots of smoke and everything like that. Of course, we were lucky. A couple weeks before, they blew the top off of one of them. They put too much stuff in it, it exploded during class. Hey, real world. I have a lot of respect for firemen. You know, had to do that job. Not fun. Not a fun job. All right. So, boiling point. Now, the thing is, when you condense out, say out of glass, You know, you got your iced tea out. You know, there's the picture, right? You get the commercial with all that nice water on the outside. Well, where's that water coming from? It comes from the air. It doesn't come from the inside. Some people say, oh, it comes from the glass. Well, let's hope not. You know, glass usually doesn't let liquid through. It's coming from the air. Well, let's see, when that molecule of gaseous water is in the air and touches, well, where is all that energy going to? It's going into my nice cold drink. And since I'm putting energy in my nice cold drink is not going to be nice and cold anymore. The temperature's going up. So in other words, do you really want all that liquid on the outside of your nice cold drink? No. Because that liquid's heating up. There we said, where's the energy? It goes in the environment. It condenses out on the glass, it goes in. And this is a radiator, right? And the radiator, this is what the radiator is doing. The steam becomes water, it condenses the water and releases the energy to the room. Great for your room, not great for your iced tea. You know, this is why the idea of the little cozy, the little rubber thing, because rubber's an insulator. Prevents this from happening. It's colder on that insulated glass. Condensation. Remember, it happens below on that. Boiling or vaporization. Now there's two ways liquids become gases. One is by boiling. Boiling occurs at the boiling temperature, BP, boiling point. This occurs at the boiling point. This is a cooling process for the material being boiled. In other words, the temperature would normally go down. Because, let's think about this. To keep something boiling, I have to constantly do what? Heat it. Because as soon as I take that boiling pot of water off the burner, how long does it take to stop boiling? A long or a little time? Not long. Yeah, it stops boiling pretty quick, depending on what kind of metal your pot is made out of, because that's where it's drawing the energy from. So as soon as all that energy is gone, it stops boiling. Temperature goes down. I mean, it's amazing how quickly the temperature goes down. Now, why does this happen? Well, let's think about this. Temperature is the average, right? The average. When something boils, that means it becomes a gas and it leaves. Are these going to be the high temperature molecules in that average or the low temperature molecules in that average? So the high ones. They leave. They take lots of energy with them. They leave the water. That's what gases do. They leave. And when the high energy ones leave, what happens to the temperature of the rest of it? Goes down. You took the high energy ones. It's like if I did the average of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I took that average. And then I do it, okay, I'm going to take away 10. What's the average of 1, 2, 3, 4, 5, 6, 7, 8, 9? What happened to my average if I took away 10? It goes down. So I took the big one out. That's what boiling does. Got to keep going. Anyone need more time? We got a picture. So first of all, in order to keep this boiling, I got to keep energy going in because energy is going out the top. The question is, where does the bubble form? And this is the big difference between boiling and evaporation. Boiling, and this is something you should add, the phase change occurs below the surface. Those little bubbles in your boiling water. What is inside of the little bubble? And it ain't air, because where would the air come from? There ain't no air in that water. What's in the bubble? What do we say happens to a gas when a liquid becomes a gas? When a liquid becomes a gas, the molecules get really far apart. And there's lots of, S word? Space. Well, if I was in the middle of some liquid, and all of a sudden I formed a lot of space, what would that look like? It would look like a bubble. because you'd form a sphere. I'm going to form a sphere of gas. We call that a bubble. Now it goes up because when I expanded it, what happened to its density? It went down, and it will go up. Get less dense flows. Steam. This is what's inside. There's steam inside the bubble. There's no air. In fact, what if I was boiling I had gold here and I boiled gold? What would be inside the bubble? Gold. Gaseous gold. It's what smelters try to avoid. Happens sometimes. They try to avoid when they're melting the gold to get it to a point where it turns into a gas, because then it floats away and they have very, very gilded beams, gilded lungs. That would be kind of nasty, breathing in gaseous gold, because when it got into your lungs, it would do what? It would condense, right? Not only give up some heat, but what would it do to the inside of you? It would plague your insides with gold. You'd be probably a dead person if you did it enough. However, metal vapor is very bad. This used to happen with mercury. Like they wouldn't plate their things, but they get mercury vapor and get into their system. Mercury vapor causes lesions in your brain. This is why hatters, the term Mad Hatter, was a common Victorian term because people who made hats, they cured the pelts, like the beaver skins, in mercury solutions, and they would, over time, they would absorb all this mercury and it basically make lesions in their brain, which makes them go mad. And this is where the idea of the Mad Hatter in Alice in Wonderland came from. So that was a term, mad as a hatter. That was a very common term, you know. That was not very much like Johnny Depp. Now last thing here, evaporation. This is also liquid to gas. This occurs at the surface of the liquid. It also occurs below the boiling point. However, remember how we talked about in the condensation that the molecules undergoing condensation below the boiling point, that those individual molecules did have the kinetic energy with associated with boiling point. The molecules that undergo evaporation have that 100-degree kinetic energy. This is why they become a gas. You have to have that energy to become a gas. But just like boiling is a cooling process, evaporation is a cooling process. That same idea. If I take the high energy ones out of the water, what's going to happen to the temperature of the water? It's going to go down. This is how your body cools itself. Your body puts water on the outside of your body. That water evaporates, and when it evaporates, it takes heat away from your body. You know, this is why certain things, you know, people, oh, I'm going to wear this plastic suit to work out and I'm going to sweat a lot. Well, that's a good way to basically kill yourself by heat things. Because your body, you're trapping all that energy inside. You can't do that. It's also a problem when it's humid out. It's really humid, miserable. If you've ever been in a humid environment, it doesn't evaporate. When we talk about relative humidity, we'll talk about that. This is why, you know, you go outside in like back east. You know, we did PT like at dawn, right as the sun went up, because otherwise you wait too long, it's just horrible. You're going to do that. Of course, we do our marching at night after the sun goes down. That's even worse on that. How many have been to Disney World in the summer? You know, the sun goes down, although the sun is not beating down on you, is it nicer? No. Is it worse? Yeah. There's a reason for that. You know, it's more miserable at night than it is during the day sometimes. Although at least during the day you don't get the direct sunlight, but still it's on that. All right. So I have a little video for you. And here.
Eureka! The story so far. As the molecules in a solid get hotter, they vibrate faster and faster, until their mutual force of attraction is no longer strong enough to hold them together. This causes them to slip out of their latticework pattern, which therefore falls apart. When the latticework of molecules in a solid has collapsed, we say that the solid has melted. It has changed from a solid state into a liquid state. And now, evaporation and condensation. The trouble with goldfish bowls is that every few days, you have to remember to fill them up with water. Why? Where did all the water go? How did it just vanish like that? Well, why don't you fill the bowl up and dive in so that you can see for yourself what happens. Water is a liquid, so its molecules are moving too fast for their mutual forces of attraction to keep them together in a regular latticework. So they're slipping and sliding all over the place. Although the molecules are packed about as tightly together in a liquid as in a solid, in the liquid state, there is complete disorder, and it's every molecule for itself. Some molecules end up being jostled about at the top of the liquid. They, in fact, form the surface of the liquid. Every now and then, this jostling forces an individual molecule to pop out of the liquid altogether, and it escapes into the air. Of course, over time, many millions of molecules escape from a liquid in this way. This continual popping out of molecules is rather like the movement that goes on in a popcorn machine. Only in the case of molecules, most of them stay up in the air and now fly about with complete freedom. No, of course you can't see them now. One of these little lumps on its own is so tiny you couldn't even see it with a microscope. You can only see molecules when billions of them are crammed together in the form of a solid or a liquid. You can see them when they make up the water in your goldfish bowl. But as soon as they escape into the air, they become invisible. But they're still there flying about. Only they don't form a liquid now. They form an invisible gas or vapor. That's why what happened to the water in your goldfish bowl is called evaporation. A change of state took place. The water changed from liquid to gas. It became water vapor. Water is continually evaporating. In fact, if you left your goldfish bowl out in the sun, the water would evaporate even faster, because the warmer the water, the more rapidly the molecules jostle each other, and the more often they pop out into the air. So if you're tired of continually having to top up your goldfish bowl, one solution would be to make the water as cold as possible, so that the molecules will move more slowly, and therefore the water will evaporate more slowly. But now what's happened? Now you can't see your goldfish. How come? Well, as soon as the water vapor molecules in the air come in contact with the cold fish bowl, they become colder as well. And the colder molecules get, the slower they move. And the slower they move, the less they can resist their mutual forces of attraction. So they start to crowd together more and more tightly. In other words, the gas becomes a liquid again. The water changes back from its vapor state into its liquid state. And it's this water which collects all over the surface of your fish bowl. That's what clouds it up. Since the change from vapor to liquid is caused by the arrangement of molecules becoming more and more dense, this change of state from vapor or gas to liquid is called condensation. So when water isn't evaporating, water vapor is condensing. You can't win with goldfish bowls. Have you ever thought of keeping a cat?
All right, I think that, yep, that's it. So